Welcome to this video on conditional statements and loops in R. A conditional statement is something which allows us to say, if our data meets this criterion, apply this action or this function. If it meets this criterion, then apply this function, and otherwise apply this function or do nothing. Loops allow us to apply a function or set of functions across different collections of data equally and quickly. So, for example, if we have several thousand data frames, we can loop over every single one of those data frames to collect the same information from each one without having to do it one by one. So we're going to start off with the if-else conditional statement, which is similar to the if statement that you might be familiar with in Excel. So the function is if-else, and then we supply three arguments. The first argument is a logical statement, so it could be a comparison, so is 4 greater than 5. The second argument is what we want R to do if the condition evaluates to true. So we can ask for it to print out the character vector yes. And the third argument is what we want R to do if the conditional statement is evaluated to false. So we'll ask it to return another character vector, no. And then if you hit Control and Enter to run this code, then of course it prints no, because it looks at the conditional statement, the first argument, 4 is greater than 5. This is false, and so it returns the third argument, no. And just to show the other way around, if we change this so that we say 5 is greater than or equal to 4, then of course this evaluates to true and it returns yes instead. Now we've just returned character vectors, yes or no, but of course you can do much more complicated things if you want to, like putting a function in here, and if this evaluates to true, then R will look here and perform the function however you've defined it. Now that's great if you have a conditional statement that you want to test and you just want a binary decision, so either do this thing or do this thing. But sometimes we want a little bit more control over our conditional statements, and the if statement is a way of exerting finer control over what happens. So if we define two variables, a and b, a is equal to 4, b is equal to 5, and then to start an if statement we just type if, and then in brackets we give the conditional statement to the logical statement to evaluate. So we'll say that a is smaller than b, which of course is true. Following the brackets we open a set of curly brackets, and then it's inside these curly brackets that we tell R what to do if the logical statement is evaluated to true. And convention says to make these if statements a little bit easier to read, we usually put this next section on a new line, and you can see that RStudio has already put the closing curly bracket on the line below. And the code has been indented so that we can easily see that whatever we write on this line is part of the if statement. So let's say that if a is smaller than b, return a divided by b. And then if we run this if statement, we get the output of 0.8 because a is smaller than b. So R evaluates this to true, and because it's true, R then executes the code inside these curly brackets. If a was equal to 5, and we run this, nothing happens. So R evaluates this to false, and because this is false, the code within the curly brackets is not run and nothing is returned. Now, like above, sometimes we might want R to evaluate a logical statement, and if it's true, perform one action, and if it's false, perform another action. Now you can do this with the if-else statement that we started with, but you can get a bit more fine control if you combine the if statement, as we've used it here, with a separate else statement. So I'll show you how that looks in a second. So we'll start with a similar looking if statement as before. So if A is smaller than B, close the parentheses, and then we open up a curly bracket because this is where the code is going to go if the logical statement evaluates to true. And then if this is true, we're going to ask R to perform the paste function. So the paste function is useful because it allows us to literally paste together different sections of output. So for example, we can paste together a character string. So we want to output to the console the string b divided by a is equal to, and then with the paste function, if we separate the arguments with a comma, it'll paste together all of the elements that we've separated by a comma. So then we want to paste with this character string the value of b divided by a. Let's just set a back to being 4. And then I can show you actually what this will look like with the paste function. So if we run this snippet of code, R looks at this logical statement, a is smaller than b, it evaluates to true, and so it runs the code in the curly brackets. And so what happens here is R pastes together the character string, b divided by a equals, and the actual value of object b divided by object a, which is 1.25. So it's pasted these two together to make a single message at the bottom of the screen. So it's useful to use this paste command sometimes to produce human readable output messages. But if this evaluates to false, we want R to output something different. And so we're going to use the else command. So the way that this works is that on the same line as the closing curly bracket, and this is really important, otherwise it won't work. So on the same line as this closing curly bracket, we type the word else and open a new curly bracket. And again, convention says that we start the body of this else statement on a new line. And so if this evaluates to false, instead we want R to paste a divided by b equals, separate with a comma, and then instead we want it to perform a divided by b. And so what will happen is if a is smaller than b, this evaluates to true, and R executes the section of code in the curly brackets for the if statement. And then it stops. It doesn't execute the else statement. If this statement evaluates to false, it ignores the curly brackets after the if statement and instead goes straight to the else statement. And so if we run this code, we get the same output as we had a second ago. But if we change this around, so if we make a 5 again and run the code, instead of having a divided by b equals 1.25, we see we have instead of having b divided by a equals 1.25, we have a divided by b equals 1. It's ignored this section of code and instead has run this section of code. So again, this is an instance where we basically have a binary outcome. If this is true, perform this. If it's false, perform this. But sometimes we will have perhaps 3 or more different outcomes or results that we want, depending on our logical statement. And we can achieve this using the ElseIf statement, not to be confused with the if-else statement. So I'm going to copy this section of code, this if statement, just to make things a little bit quicker for ourselves. And after this first if statement, so before the else, put this onto a new line, we're going to add an else if statement. So the else and the if are 2 separate words. And then we basically treat this like a normal if statement. So we open standard brackets and give some kind of logical statement inside. So let's say a is equal to, remember the double equals means is equivalent to, b, close the round bracket and then open curly brackets. For a second, we're just going to delete the closing bracket because we'll add it in a second. Because we'll add it back in a second in front of the else statement. And then if we go into a new line, let's say that if A and B are equal, we want R to print A and B are equal. And then on the new line, we'll put the closing bracket for the else if statement. So what will happen so far is R will evaluate this expression. If it evaluates to true, it will run this code and only this code. If this code is false, it will skip this code and instead will look at the logical expression that we've given the ElseIf function. So this is basically saying if this is true, do this, else if this is true, perform this. And then if this is evaluated to true, it will perform this code and only this code. If this evaluates to false, then finally we rely back on the else statement to perform this code regardless of what else has been evaluated. For that to happen, the else needs to be on the same line as the closing bracket of this else if statement. And so we've got our initial if statement, our else if statement, and our else statement. So we have three possible outcomes. So if we set this back to 4, this if statement evaluates to true, and we get the result of this. B divided by A is 1.25. If A and B are both equal to 5, this code is not run because A is no longer smaller than B. This code evaluates to true, and so we get A and B are equal. And the final else code is not run. If A is equal to 6, then hopefully you can see that what will happen is the else statement will kick in and we get A divided by B equals 1.2. So we're just sort of performing very minor operations, pasting some text and a quick division together. But I hope that you can see that, for example, you could use this to, you could give it a vector of data from your data frame and ask it to apply certain operations or transformations to the data or to select certain data depending on whether it meets certain criteria. And you can make these if statements more complicated and add more if and else if statements inside them if you want to perform 4, 5, 6 or even more different operations depending on what the data evaluates to. Sometimes we want to perform functions or actions while a particular condition remains true, and we can do that using the while statement. So the while statement is sort of what it sounds like. So you start it with the word while, open parentheses, and then you give it a logical condition to evaluate. So for example, while number 1 is equal to number 1, just like the if statement, we give the curly bracket. Convention says that we put the next code onto a new line, and let's say we want to print this is true. Notice this time that we are explicitly wrapping this character string inside a print function. There's a difference in R between printing something, such as text, and returning a value. If you run the code that we're about to run without this print function, you won't actually, R will return the value, but you won't actually see anything printed to the screen. So I'm just simply using this so that we see this text printed as a message. Difference between returning and printing is that, say we were to save this as an object, if this function returns a value, then that will be saved as part of the object. Whereas if we print something, it's not actually saved to anything; it's just printed out onto the screen. And so if you hit Control and Enter on this, basically forever and ever, R will continue printing this is true, this is true, this is true, because of course the number 1 is always and forever going to be equal to number 1. If you get into an infinite loop like this, which is not a good thing usually, you can either click this stop button or just hit escape, and R should stop. So I've used this just to illustrate what while does, but try not to get yourself into infinite loops like this. And so what I hope you can see happened is R evaluated this statement. If it evaluates to true, it performs the code between the curly brackets, and then it goes back to this statement again and evaluates to see whether it's still true. And of course, after printing this is true, maths remained the same and number 1 was equal to number 1 again. But this while statement is useful for wrapping functions or wrapping code in here that changes or may change whether this statement evaluates to true or not. So let's take an example to make it a bit more clear. So let's initialize 2 objects, x, which is equal to 1, and y, which is equal to 10. And let's make a while statement that says while x is smaller than y, open curly brackets, print x is smaller than y. And then we're going to modify x, and so we're going to say that we're going to overwrite x, and the new x that we're creating is going to be the current x plus 1, and then the closing curly bracket. And so what will happen is R will evaluate this conditional statement, which in the first instance will be 1 is 1 smaller than 10. This evaluates to true, and so R executes this first line, and it will print x is smaller than y to the console, and then it will run the second line, which creates a new x, which is x plus 1. Once it's done that, it will go back to this statement and evaluate whether it's still true, which it will be, because now it will be is 2 smaller than 10. It's true, so it will print this, and then it will increment x by 1 again, and so 3 is smaller than 10, 4 is smaller than 10, and it'll keep going until x is now equal to 10. This will evaluate to false, and the whole loop will stop. So if we run this, we get x is smaller than y, x is smaller than y, and it keeps going until x is incremented, and actually you can see over here in our global environment that now x is equal to 10. So the while statement is useful if you want to repeatedly apply an operation or a function which changes the original variables that you supply to the while statement, such that the operation is performed a certain number of times, and then until this condition evaluates to false. Now sometimes we might want to apply a function to every object which is part of a list or part of a data frame, and we can do that using for loops. So let's create an empty vector called result. So if you just use this, you should remember the C function, the combine or concatenate function that we use to create vectors. If you assign the result of this combine function to an object, then it will create an empty vector with nothing in it. And now what we want to do is fill this empty vector with the values of the numbers 1 to 5 squared. And we can do that with a for loop. The basic structure of a for loop is that we call for, and then we open brackets, and then we supply curly brackets. In the standard brackets, the first argument, or the first thing that we want to state is the object, or the unit that we're going to apply our function to. Now actually this can be whatever we want. We can name it whatever we want. A common convention is to say I, which sort of stands for index, or you can use words which make it a little bit easier later on for you to come back and understand what it was that you were iterating over. So it could be for subject, or mouse, or in our case we're going to say number, and then you use the word in, and then you supply the list or vector or the structure which holds all of those elements that you want to iterate over. So for us, it's going to be the vector 1 to 5. So far what we've got is we're telling R that for every number in the vector 1 to 5, apply whatever is within these curly brackets. Again, we call this number because it's an easy way of remembering exactly what it is that we're iterating over. A common thing, as I said, is to use the letter I, just because it stands for index and it's a bit shorter than typing out number each time. So actually we're going to stick with that because this is a slightly better convention. And then inside these curly brackets, we're going to supply the function that we want to apply. And again, convention is that we put this onto a new line. And we're going to say that for the ith element in result, assign this to be I to the power of 2. So what will happen is for every number in 1 to 5, we start with number 1. The code that is executed is actually result index number 1. So the first element of the result vector is equal to 1 to the power of 2. Then we go to the next element, which is number 2. So result index 2, the second position in the result vector, is equal to 2 to the power of 2. And then we do the same for 3, 4, and 5. And so if we run this, and then look at our result object, we have 1, 4, 9, 16, and 25. So 1, 2, 3, 4, and 5 squared. And again, we used I, but we could have said for every number in 1 to 5, the result indexed by number is equal to each number to the power of 2. And we get the same result. So what you use as a name doesn't matter, so you can either use something more verbose to remind you what it is that you're iterating over, or you can just use I. It doesn't matter. Now we can combine for loops with if statements. So for example, we could iterate over every number in 1 to 5, and for each one of them ask the question, if this number passes some kind of test, apply this function. So we'll start with our for statement. So the same as before, for I in the vector 1 to 5, close bracket, open curly bracket, and we're going to say if I modulo 2 is equal to 0. So this is probably a new function that we've encountered, a new operator. 2 percentage marks is the modulus operator. And what this means is divide this number by this number and return the remainder. So for example, 4 modulus 2 is 0 because there's no remainder left over when you divide by 2. And so what we're basically asking here is if I is an even number. If it's an even number, this value will be equal to 0, and if it's not an even number, then it won't be equal to 0. And so if this is true, we want to return I is even. Else I is odd. And so I hope you can see that all we've done is wrapped this if and else statement inside a for statement. And so every single element in the vector 1 to 5 will be passed through this if-else structure to see whether each element is even or odd. And so if we run this, oops, I forgot to wrap these in a print function, because of course it returns the value and doesn't actually print it to the console. If we rerun this, then for number 1 it says I is odd, for number 2 it says I is even, And so for each element in the vector 1 through 5 is passed through this if statement, and we get an output for it. Now, if you go on to Stack Exchange or any of the R forums looking for help with your for loops, you'll often find that a lot of people, and sometimes unhelpfully, tell you, don't bother with for loops, just use the apply family of functions. There's a couple of reasons why people tend to prefer the apply family of functions over for loops. We'll look at some examples in a second. One of them is that sometimes, not always, but sometimes the apply family of functions are quite a bit faster than using for loops. If you're iterating over tens of thousands of elements, apply family functions can be faster. Another reason is that actually they tend to be much more concise, much easier to code. You can do on a single line what it might take you 6 or 7 lines to achieve with a for loop. And finally, apply family functions are considered safer because whereas a for loop can change a variable that is already in your global environment, the apply family functions don't do this. Which it may not be overly obvious at the moment why that's important, but it can be useful for avoiding making mistakes and modulating variables in your environment that you actually didn't want to modulate. So they're called the apply family of functions because there are lots of them. So apply, lapply, sapply, vapply, tapply, mapply. We're just going to look at 3 of them: lapply, sapply, and apply, and look at instances where they can be used instead of using slightly more complicated for loops. So let's start with lapply. So what does lapply stand for? It basically means apply a function to a list of objects. So to every element of that list, apply a function and return a list. So the L stands for list apply. So it takes a list as input, applies a function to every element of that list, and then returns the output as a list as well. So let's just initialize an empty list like we did with the vector before. So for I in 1 to 1,000, define a variable called norm, an object called norm, and I want this to be a list of random normal values, 10 of them for each list, with a mean of 0 and standard deviation of 1. So what this looks like on its own, these are 10 random samples from a normal distribution with a mean of 0 and a standard deviation of 1. And the fact that we've wrapped it inside list means that this is a list of length 1 with 10 elements inside it. And then we're going to update my list by combining my list, which initially contains nothing, with our list of length 1 containing 10 values from our normal distribution. And then we close the curly bracket. And so what will happen is that for every element in the vector of 1 to 1,000, basically 1,000 times, I was going to generate a list of length 1, which contains these random samples from a normal distribution, and then it's going to combine those values with the existing values in my list. So at the moment there's nothing in my list, it's an empty list. When we do this once, it will be a list of length 1 with these 10 random values in it. When it does it again, those values will already be there, and we're going to add the new values that we create when we do this the second time. And so if I run this code and we call head on my list, and we'll just see the top 3, basically we've got the first element of the list is a vector of 10 random samples from the normal distribution. So is the second item in the list. So is the third item. And this has gone on for 1,000 times. Okay, so that was just to produce a list of vectors from a random normal distribution. Now we want to extract the mean value from every single list element. So from every single sample of 10 values. And so we can do that using for loops. So we say for I in, and what we can do, we could say 1 to 1,000 because we know that there are 1,000 elements in a list, but actually often we don't know exactly how many elements that we have. And so what we can say is in the vector 1 to whatever the length of my list is. And actually if we run just this little snippet, we get the vector 1 to 1,000. So this is the same as typing I in 1 to 1,000. But for the sake of being good programmers, we're going to say 1 to the length of my list. And we want our list means indexed by I. So the ith element of our list means list, the list that we created to hold the output of the data, is going to be the mean of my list indexed by I. And remember that when we index a list, we always put the index in double square brackets. And that if we run this and call head on list means, we get the first 6 means from our list of random samples. Now it took us a little bit of thinking to come to this. This is far more complicated actually than it needs to be. We can do this with far fewer characters and on a single line using ElseIf. So let's just create a new object called list means 2 to hold the data, and to this we're going to assign the output of ElseIf. And the way this function works is that you supply the object that you're going to iterate over, so my list, and then you supply the name of the function that you want to apply to each element of that list, and hit Control Enter. And then if we call head on list means 2, you'll see that we get the identical results as we got with the for loop. So for each element in the list, we get the mean of those 10 values that were randomly sampled from a normal distribution, and these values match up to the data that we produced using the for loop. And so hopefully you can see that by doing this, we take out a lot of the hassle and a lot of the thought into how to produce this output compared to using this. And the code is much neater. It's easier for us to see exactly what it is that we're doing, and we're not in danger of altering any of our variables in the global environment. So for example, we could have done something inside this for loop that, without us realizing, altered the original mylist variable, whereas the ElseIf doesn't do this, and instead returns the output which we then saved to a new object. Now the output that we got from ElseIf, as in the for loop actually, is in the form of a list. You can see that we have the first, second, third element of a list of individual values. Lists are good for holding data, but actually often we like to work in vectors because vectors are a bit easier to work with as a form of data, and also you can view a far greater number of elements in a single vector than you can in a list, because a list is printed down the screen, whereas a vector is printed across the screen. And so often we can get an output of a looped function by using ElseIf. And the S in ElseIf stands for simplify. And so all ElseIf does is the same as ElseIf, but it tries to return the output as a simplified vector instead of a list. So if we just copy and paste this line of code, we'll call it list means 3 and change the L to S and hit enter. And then if we call list means 3, then we see that we get the mean for each element of our original list printed as a vector, which is much more amenable to us manipulating it as a form of data and also of actually interrogating all of the values. One word of warning with ElseIf: although it will try to simplify the results into a vector, depending on the data structure that you give it, it might not always be able to. If it's not able to, instead of giving you an error, it'll just sort of do the best that it can, which may sometimes result in you getting something unexpected. So if you're using ElseIf, which is fine, always check or validate that the output that you're getting from it is actually what you want. Now, the very last thing in this video is I want to talk to you about the apply function, because often we want to apply a function over every column or every row of a data frame. So if we're working with data, it's quite common that we may want to apply a certain transformation or get some summary statistics from rows or columns of our data. And you can do that with the apply function. So apply really is for performing operations over rows and columns of arrays or matrices, but we can use it for data frames as well. So let's use the data function to load in our favorite iris data frame. And let's say that we want to get the mean of every column or every numeric column in our data frame. So let's just remind ourselves of the iris data frame. So we've got these first 4 columns of numeric data and then a 5th column of a factor. And so let's apply data to iris, all of the rows and just columns 1 to 4 because we don't want this species column. So similarly as for ElseIf and ElseIf, the first argument is the object that you want to iterate over. The second object is basically where we tell apply whether we want to iterate over the rows or the columns. If you want to iterate over the rows, we supply the number 1. If you want to iterate over the columns, you supply the value 2. So we're going to start with the columns, and then you finish with the function that you want to apply. So we'll apply the mean function. And if you hit Control and Enter, you can see that for every column, R has returned the mean of the entire column. If instead we wanted the mean of every single row, we just change this to the number 1 to tell apply to look at the rows instead, and then we get a vector of the row means. So that was a very brief introduction on conditional statements and loops in R. We only sort of kept things very, very simple, but I hope that you can see that you can, if you have a basic understanding of each of these building blocks, you can use them to make quite succinct interrogations of your data and to make sometimes quite complex decision structures for applying certain functions to certain kinds of data quite quick and intuitive.